Polynomial weights algorithm. The polynomial weights PW algorithm is a natural extension of the RWM algorithm to losses in a closed interval between 0 and 1, or even to the case of both losses and gains. See exercise 4.4 that maintains the same proof structure as that used for RWM, and in addition performs especially well in the case of small losses. Polynomial weights PW algorithm. Initially, Wi to the t equals to Wi to the 1 equals to 1, and Pi to the 1 equals to 1 over n for I in x. At time t, let Wi to the t equals to Wi to the t minus 1 times 1 minus tau times Li to the t minus 1. Let Pi to the t equals to Wi to the t over capital W to the t, where capital W to the t is the summations of Wi to the t, summing for all those I in x. Notice that the only difference between PW and RWM is in the update step. In particular, it is no longer necessarily the case that an action of total loss L has weight 1 minus tau to the L. However, what is maintained is the property that if the algorithm's loss at time t is f to the t, then exactly n tau times f to the t fraction of the total weight is removed from the system. Specifically, from the update rule, we have capital W to the t plus 1 equals to capital W to the t minus the summations of tau times Wi to the t times Li to the t, summing for all those I, which is equals to capital W to the t times 1 minus tau times f to the t, where f to the t is equals to the summations of Wi to the t times Li to the t, summing for all those I over capital W to the t. So f to the t is the loss of a PW at time t. We can use this fact to prove the following. Theorem 4.6. The polynomial weights PW algorithm using tau less than equals to 1/2 for any 0, 1, the closed interval between 0 and 1 valued loss sequence, and for any k has LPW to the t is less than equals to LK to the t plus tau times QK to the t plus ln n over tau, where QK to the t equals to the summations of LK to the t squared, summing for all of those t starting from 1 to capital T. And if we set in tau equals to the minima chosen between the square root of ln n over t and 1/2, and noting that qk to the t is less than equals to capital T, we have LPW to the t is less than equals to L min to the t plus 2 times square root of t times ln n. Proof: as noted above, we have W to the t plus 1 equals to W to the t times 1 minus tau times f to the t, where f to the t is PW's loss at time t. So, as with the analysis of RWM, we have W to the t plus 1 equals to n times the multiplication of 1 minus tau times f to the t, multiply for all those t starting from 1 to capital T, and therefore ln of W to the t plus 1 equals to ln n plus the summations of ln of 1 minus tau times f to the t, summing for all those t starting from 1 to capital T, which is less than equals to ln n minus tau times the summations of f to the t, summing for all those t starting from 1 to capital T, which is equals to ln n over tau times LPW to the t. Now for the lower bound, we have ln of W to the t plus 1 is greater than equals to ln of WK to the t plus 1, which is equals to the summation of ln of 1 minus tau times L k to the t, summing for all those t starting from 1 to capital T. If we use the recursive definition of weights, which is greater than or equals to minus summations of tau times L k to the t, summing with t starting from 1 to capital T minus the summations of tau times L k to the t, such a term, the square of such a term, if we summing for all those t starting from 1 to capital T, using the inequality ln of 1 minus z, which is greater than or equals to minus z squared for 0 less than or equals to z less than or equals to 1 half, which is equals to minus tau times ln k to the t minus tau squared times qk to the t. Combining the upper and the lower bounds on ln w to the t plus 1, we have minus tau times lk to the t minus tau squared times qk to the t less than or equals to ln n minus tau times lpw to the t, which yields the theorem.